Thank you very much for the kind introduction. I'm very happy to be here with you to share this work with you. This is joint work with Marie-Claude Vachon. She's my former PhD student. She was my student at UQAM. I will start right away and explain why we're looking at this specific optimal stopping problem with a discontinuous reward function. I'm looking in this work into a specific insurance. It's a hybrid product that mixes insurance guarantees and financial guarantees. It's called a variable annuity or segregated fund in Canada, and it's a product that's within this bigger family of equity-linked insurance products. So basically, and I want to talk just a little bit about how this works because it really informs a lot of the later intuition in this problem. So the way it works is that a policyholder will use this typically to accumulate wealth for retirement, usually. And they will invest an initial premium. This contract that we're looking at is very simplified compared to what you actually see in the market, but we wanted to look into surrender incentives. And so the policyholder will invest an initial premium, and the insurance company that issues the product will take this premium and invest it completely in a risky asset. So typically this will be a fund that tracks the market, that tracks the S&P 500, for example. The policyholder is guaranteed that at maturity, they will never receive less than a predetermined amount G. A predetermined amount G. So here, G is just a constant, and FT is the stochastic process that represents the value of this investment account through time. At maturity, the policyholder will receive the maximum between this guaranteed amount G and the value that is accumulated in the investment account. And so this function here, phi, is really it gives the benefit at maturity. An interesting feature of this is that the policyholder can surrender or lapse the contract before maturity. Basically just say, I changed my mind. I no longer want to wait for the whole duration of the contract. I don't really care anymore about the final guarantee. I just want my money that's accumulated in the account. There's different reasons why one would want to do that. In that case, they can receive the amount that's accumulated in the account, but typically there will be a small penalty charge, a few percent of the amount invested in the account. And typically this percentage, so the charge, will decrease through time. So the insurance company will want to put a bigger penalty for surrenders that occur early in the contract compared to surrenders that occur later. And so the amount that's received upon surrender, so upon, let's say, exercise of this guarantee, but before maturity, will be less than or equal to the value FT of the investment. And this is maybe common to various equity-linked insurance products. And one of the specificities of this type of product of variable annuities is that this guarantee is paid for via a fee. So the fee here is denoted by C, and it's paid out of the account. We assume that it's paid out continuously, and it's similar to a management fee, for example, if you've invested in some kind of mutual fund. So it's a percentage of your return usually, which will decrease the actual return on the investment. Typically, this guarantee fee is a fixed rate. You'll have, for example, 0.75% or something. In this work, we'll assume that the fee can actually be dependent on time and or on the value of the investment account. Okay, so it can be time or state, we call it state dependent. And the reason why we want to look into this is because in the literature and in some of my previous papers, I've looked at problems like this, from a numerical perspective. And it's also been seen in the industry. So certain products will have a fee that can be, or it's already been proposed to have a fee that will be time or state dependent. And this really has an impact on the surrender incentives. So our goal was to check how the guarantee fee and also the form of the surrender, the penalty charge, how it impacts the surrender incentives from a theoretical point of view. So we've done it numerically, but for various reasons here, we wanted to look at it theoretically. So this, in the title, I have this discontinuous reward function, and this is the reward function here. And it has a discontinuity, so it has two characteristics. First of all, it's time dependent because it changes whether you look at the function at maturity, capital T, or before, but it also has this time dependence in the penalty fee because the penalty fee will typically decrease through time, change through time. So the reward function is time dependent, and there is a time discontinuity at T because this function G tilde here will always be or is bounded above by X, right? And if X is less than G at maturity, there's a jump. So I'll show an image after. These features, the fact that this reward function has these specificities are often overlooked in the literature on variable annuities. And what I mean by that is that there's this other optimal stopping problem in finance, which is the American option. So if you know the American option, what an American option is, you know that the reward function is not time, does not depend on time. And the reward function is also continuous. And so for those who don't know what an American option is, you don't have to worry about it. Just know that, like I said, the reward function is a bit different. In the literature on variable annuities, what people typically do, and by people I mean me and others, but here I want to talk about what we did in the past. We just took numerical methods that were developed to solve the price of the American option, to find the price of the American option, and we applied it to this problem. And without being sure that it can work, because we disregarded these specificities. So in this work here, we wanted to first confirm that what we had done in the past was still held. And we also wanted to answer some more questions that I'll talk about in a second. So these here are the paths of the different possible trajectories for the reward function. So in blue, this is the case when the investment performs well. The guaranteed amount is at 100 here. So when the investment performs well, then the path of the reward function is, so the reward function here is continuous. But when there's a problem or when the performance is low, it's possible that the investment at maturity is worth less than the guaranteed amount. And then in this case, there's a discontinuity exactly at maturity. So that if the policyholder was to lapse the contract the day before maturity, they would receive much less than they would if they waited a full day for the guarantee to be triggered. And it's really because the guarantee is only triggered at maturity that there's this discontinuity. These are some examples from the literature. I said it before. I used different numerical methods to solve these problems. Other authors have done it too. There's, in certain cases, especially in the case of the integral representation and expressing also, so optimal stopping problems, their solution can often be linked to the solution of a free boundary problem, free boundary value problem. Doing that, this is what we did, and we solved then the free boundary value problem numerically. But this link, I wanted to confirm it. We wanted to confirm it in this paper. We know it exists for the American option, but for this specific problem with the discontinuity in the reward function, we wanted to confirm that it was correct to do it. Just to give you also an idea, further motivation of why we wanted to look at this problem is an example from a paper. This is a paper from my PhD thesis, and we in this specific work, we were looking at a fee for this kind of variable annuity, a fee that is paid at a fixed rate, let's say 1.5%, but only when the value of the investment is below a certain threshold. It doesn't really matter which one, but only in a certain region, basically, in the plan. And so this is the fee function that we fixed in this paper and that we looked at numerically. We analyzed this numerically, and we looked at different surrender charge function. In this image here, there's no surrender charge, and what's in gray represents the surrender region. So basically, at time 0, the value of the investment is worth 100, and as soon as these trajectories that I drew before in the previous image, as soon as the trajectory enters the surrender region in gray, this means that optimally, in order to maximize the value of the contract, the policyholder should surrender the contract. And so when there's no surrender charge, we see that this is the optimal surrender region. But when we add different types of surrender charge, so in this case, we have a surrender charge that decreases to reach 0 just or at maturity. And in this case, we have a surrender charge, but only for the first 10 years. For the last 10 years, there's no more surrender charge. And we see that we observe two things in this image. First of all, for a period of time, a few years at the beginning of the contract, we're able to completely eliminate the incentive to surrender optimally. And so this is really done by playing with the interaction between the fees and the surrender charge. And something else is now these images aren't perfect because you see that there's a 150, and that was the threshold above which the fee was no longer paid. Above 150, there's no gray, and this is not a mistake. This really, the surrender region is really like this. So if you take like the section, the cross section here, you fix the time t, and you look at the values of the underlying investment account for which it's optimal to surrender, you see that there's an interval here from 0 to 130 where it's not optimal to surrender, and then there's an interval on which it's optimal to surrender, and then there's another interval in which it's optimal to keep the contract. So you have this, if I fix time, you have this disconnected or continuation region, which is not the case here. And this is so interesting on its own for just studying a bit the geometry of the surrender area, but also it has practical implications when you're trying to build or to develop numerical methods to price these kind of products, because when you know that once you reach the threshold, when you know that your surrender region has this form here on the left, then you can just say, once I found one point, I can assume that the rest is the surrender region. Whereas if you have this kind of shape for your surrender region, you can't assume that. You have to really check every point. For a given time, you have to check every value of the underlying. So this is also why we wanted to get more information on the shape of the surrender region. For example, under which condition do we have this type of surrender region? This is the plan of the presentation, and I'll go faster on some sections, but I want to talk about the problem and discuss especially existence of a trivial optimal stopping time. So we have a condition under which there's something special that I want to talk about. And then I want to talk about the alternative representation for our reward function, which is an important tool to get a few results on the value function of our problem, and then I'm going to discuss some results on the characterization of the surrender region, because we do get some conditions to have like this threshold type surrender region. The setup of the problem is we keep it simple. Our market, maybe heard of the word before, but our market is a Black-Scholes market, which means that if we didn't have the fee, our investment would simply follow a geometric Brownian motion. Now we have this fee here in red, which can depend on time or on the underlying, so we can have different forms for this stochastic process. And I'll discuss in a second a bit more information on the shape of the fee function. And we have the price of the contract at time 0. So to price the contract at time 0 and at any time t during the duration of the contract, we have to solve this optimal stopping problem. And economically, what this means is that the value of the contract is simply the expectation of the discounted benefit, so the discounted amount that the policyholder receives, given that they act optimally, that they surrender the contract optimally, or that they keep it until maturity. This is here, it defines my gain function. So it has x here. X is the value of the underlying investment, which will be penalized by the function g. And at maturity, then it's always the maximum. There's always this guarantee that applies. So the phi function returns value between 0 and 1. Okay, typically, it will return values. So it's bounded. It's nice. It's bounded. For now, I don't have any more assumptions on the phi function. I'll add assumptions as I go. But this general setting will include different shapes of the phi function that have been seen in the literature. There's a bit more structure on the surrender penalty function, because I said before, it has economical meaning, and also mathematically it helps. But the phi function or the surrender penalty should be non-decreasing. So the surrender penalty is decreasing, and the function g, that's always confusing, the function g represents a proportion of the investment that's received on surrender. And so this function g is non-decreasing, and it reaches 1 at maturity, meaning that just before or at maturity, you don't have a penalty anymore that's applied to the function. Actually, we don't need to define it at capital T exactly, but we need to define it everywhere else before. So this helps for proof to define it all the way to capital T. And the function g will be C12 with bounded derivatives. So we want it to be nicely behaved. So in particular, it will reach 1 continuously, which means that your surrender penalty will gradually disappear. And it could also have disappeared before maturity. You could have no penalty for the last year, for example. And just some terms that I use in the rest of the talk. Discounted reward process is simply the reward which is discounted with the risk-free rate, so this factor there. The value function is, so it's like always in stochastic control. The value function in this case can be seen as the price of the contract, the value of the contract. So if I fix time during the contract and the value of the underlying investment, and starting from there, I solve the optimal stopping problem. This is my value function. And finally, I will say that a stopping time is optimal for this specific value function if it's the one that returns. If when I apply this optimal strategy or this stopping strategy, it returns the value function. Maybe going back to when we first worked on this problem, our goal was to work on this problem numerically in a model that was a bit more complicated. And we wanted to make sure that the theory on which we were basing our numerical work was solid. And it wasn't obvious from the recent literature that what we were doing was correct, because all of the results we could find were using a continuous reward function. We wanted to make sure that the value function was continuous, smooth enough that we could take derivatives, etc. But all of the results we could find were using the fact that, or were under the assumption that the reward function was continuous. So for us, this was a bit of a challenge. When we found something about reward process that's discontinuous, but they wanted the process to be bounded. Our process is not bounded. And so in the end, we went back to a bit older literature, which has more general conditions, under which we were able to confirm, in this case, we were able to confirm existence, of course, of an optimal stopping time, and we were able to confirm the shape or to define this optimal stopping time. And I'll get to it in a minute, but before, I just want to talk about this condition here. The problem we're looking at, again, is akin to, or has a lot of similarities with American options. And so now I'm going to do an aside for people that know a bit more finance, but the American option, when it's written on, when it's a call option that's written on a stock that pays no dividends, then the optimal stopping time is always maturity. Basically, the American option has the same value as the European option. What we have here is similar. And what it says is that when we have this pretty complicated partial differential inequality, when this is satisfied for all t and x in our domain, then t is an optimal stopping time for one. So holding on to the contract until maturity is an optimal way of acting, and we actually show later that it is the unique optimal stopping time. And the idea here is simply that, well, when the big term on the left-hand side of the inequality is the drift of our discounted reward process. And so the intuition is that the discounted reward process on average will increase. And so we should stay in the contract because the reward increases with time. So we want to keep it as long as possible. There are some technicalities, but that's basically it. So that's a fact. So this term on the left is complicated, but you'll see that there's two terms in the middle that depend on the first and second derivative of the surrender penalty with respect to x, so to the state or the fund value. And depending on our assumptions, if we consider a simpler surrender penalty, these disappear pretty quickly and we get a much simpler condition. And this condition will reappear later, or this term will reappear later. So just keep it in mind. Here I have some intuition behind it. Not gonna get into too many details, but just want to say that basically what I had here is a generalization of a result that has been observed by various authors in different papers. So basically, when we simplify it to a fixed fee rate, a simple surrender penalty, then the condition for optimal stopping time to be the maturity is very simple. It's just like the parameter for the surrender penalty needs to be strictly greater than the fixed fee rate. And in this case, because the policyholder can expect to pay less fees in the future than what they would have to pay immediately to surrender, then the policyholder never wants to surrender, and they end up keeping their contract until maturity. This is how we see it. Now, the existence of the stopping time, so by using the general theory on optimal stopping, we're able to indeed confirm that, and this is well known, but it's just we needed to go back in the literature and confirm it. But basically, the optimal stopping time has this form. So the first time that the value function reaches the value of the reward process, then this is the optimal stopping time. And what this means economically is when the value of the contract that I hold reaches the value of what I would receive by surrendering immediately, then I should surrender the contract. So this is what we've always been using. This is what we were expecting. However, this doesn't tell us anything about the properties of this value function V. And this is what we wanted to know more about. And also in order to be able to talk about the shape of the exercise region. So we're wondering how we can get more information on this value function, and this is where we use the alternative representation. The alternative representation is simply a continuous reward function. So the discontinuity in the reward function was always the problem. Now what we do is that, so if I look at this reward process here, Z tilde, the first part is really what I had before. It's almost exactly what I had before. There's just not the maturity benefit, but the maturity benefit is actually included in this second part here. So now my new reward process is simply the maximum between what I receive on surrender and the risk-neutral expectation of the discounted maturity benefit. In economic terms, the value of the maturity benefit. It's possible to show that if I replace the reward process in my original problem, if I replace it by this continuous one, then I have exactly always the same value function. The value function is absolutely the same. And the reason why is that, so here I take the maximum between the two. Typically, so in general, H here, whenever I need to surrender, and now I'm it's not so easy, but this H here is typically at key points in time when decisions happen. The value of H will be in between the value of my surrender benefit, G, and the value of my function, or my value function here. So it will always be in between, and it doesn't really affect the value function. So I have a nice representation in terms of a continuous reward process, which will unlock many of the results that already exist. So a lot of these results that assume that the reward process is continuous, I can just use them directly here. But it raises a question. So I have the same value function, and whenever I just want to know about properties of the value function, it's fine. I can use this result. However, if I want to know something about the stopping time, about the surrender region that's associated with the value function, am I allowed to use this discounted reward, this continuous reward process? So do the optimal stopping times actually coincide? And this is not clear. Actually, we can build examples where the stopping times only coincide on a set of measure 0. Actually, we can show that the stopping times coincide. So here, tau is simply my optimal stopping time for my original problem, and tau tilde is my optimal stopping time, but for the problem with a continuous reward function. And I show that they coincide if when I stop in the modified reward process, when I stop because, or when I stop, this is my surrender benefit is greater than the value of the maturity benefit. Otherwise, if it's not the case, I set my optimal stopping time at capital T at maturity. To show that this is true, and actually what we want to know is when do the surrender regions, so the surrender regions here will define as well, the surrender regions are the complement to the continuation region, and in this case, it's really when the value function and the benefit, the reward process coincide. And if these two coincide, then the optimal stopping times will coincide at all times. And we'll see later that when I have a nice, well-behaved problem, then they will coincide. But it's not always the case. A lot of these results, then we have to put, at this point is where I start to put more structure on both functions C and G. So for example, here, if I make sure that the drift or something associated to the drift of the investment is globally Lipschitz, then I have continuity of the value function. So already this phi function that would jump from 0 to, or that would only be paid in a certain region, it's not, I'm no longer considering this in these results, which is not a big deal for me because I know that this discontinuous phi function, I can easily approximate it with a smooth function and still get those results. If I restrict myself to just functions that depend on time, so I remove the dependence on the value of the fund, I can still get interesting shapes, interesting results, and then I have more regularity on my value function. So I have some more regularity in space here. I have this result, and I have a weirder one in terms of time, but in both cases, this is sufficient to be able to link the problem to a free boundary value problem. Part of these proofs rely really on the fact that I have the modified reward process, so that I can express my value function in terms of a continuous reward process. In the paper, it goes a bit longer, but here, because these results are not very surprising, we just confirm that, yes, indeed, this, because of this nice regularity on the value function, this problem can be linked to a free boundary value problem and to a variational inequality. So if we have numerical methods that use these representations to solve our problems, then we can use them. Now, optimal exercise region, I think this is where it gets a bit more fun, because this is where we can also see the drawings. We talk about the shape of this exercise region and how do we optimally act. The main tool for our analysis is these two representations. So of the value function. Basically what this tells us is how can we interpret the price of this insurance contract that we have. And the first one is not new. This exists in the literature because we're considering a more general function. Maybe it's a bit more general, more general fees and surrender charges. It's a bit more general, but still it's a shape that we know. And if you know American options, you'll recognize it too. Basically, what we say is that the price of the contract, the value function, is equal to the value of the maturity benefit here. So the discounted value, the expectation of the discounted value of the maturity benefit, plus some premium that represents the additional value in the contract that comes from the right to surrender early. And this premium has this form here. Notice, it's not easy with this pointer, but notice this term. This term here is linked to the term we had in the big inequality on the left-hand side. This is just a simpler term because, yes, in this section, I really just look into time-dependent fee functions and surrender charge functions. So this is the first representation, surrender premium representation. It's a tool for studying the optimal surrender region, and it's also a tool for, again, if we want to develop numerical methods, this is useful for pricing this contract. I also have the continuation premium representation. So the continuation premium representation is new, and it says that the value of the contract is basically the value of the surrender benefit plus some term that I can express like this. The first part is really the value of the guarantee. So not the full maturity benefit, but really what the insurer will pay in case of the underlying investment account is too low. In the case, so only in the case that the policyholder holds it until maturity. And then there's another expression here which is not written optimally. Some parts could have been outside of the expectation, but anyway, this here in this term, we see again the term that appears on the left-hand side of the inequality, and you'll see in the next slide that this term that's here, and well, here it's the negative of this one, but this term, the sign of this term really tells us a lot about whether it's optimal to surrender or not. And I think it's kind of obvious in this case here, because if this is negative, for example, then it reduces the value of the full contract compared to the maturity benefit. If it's positive, it increases it. So that's really why this tool allows us to analyze these surrender incentives. This is my last slide of results. Then we go on to a bit of images. So a summary of our results on the optimal surrender region. First of all, I want to say, so the surrender region is S here, and if I fix the time T here, so in many cases I'll want to fix the time and see what happens at this specific time, what is the shape of the surrender region at this specific time. So the T section of the surrender region will be defined as all the values of the underlying such that this point is in the surrender region. We have this term that appeared in the expectation in both surrender and continuation premium. And if this term is negative for all T at all the times during the life of the contract, then it's not like it's a trivial problem where we need to surrender immediately. So there exists a continuation region, but there also exists a surrender region in that. So if this inequality here holds, always holding on to the contract until maturity is not the optimal surrender strategy. So we're not in the trivial case, and this makes sense because the trivial case, I think, was when the inequality here was in the other direction for all t's. So this is not the complement of the first condition, but this is part of the complement of that first condition. So in this case, this is actually the nicer case, because in this case, we know that it can be optimal to surrender before maturity, so there's some interest here. And also for every time, so at every point t, the optimal surrender region will have this so-called threshold type. So once I find a point at which it's optimal to surrender, I know that from this point on, it will always be optimal to surrender. The problem is that this point could also be infinity. So when I have this condition, it doesn't tell me there's a surrender region for every single time t. This is still something that we're trying to work on. And in this case, so when this inequality holds, then we know that the two problems, so the optimal surrender strategy with the discounted, the continuous and the discontinuous reward process, they coincide. If we don't have this inequality for all t, if we have that this same term here is, so we call it L in the paper, so if this function L here is positive for certain times in a subinterval, then in this subinterval, it will not be optimal to surrender. Okay, so whenever this term is positive, so when we observe so it has to be this compact subinterval, or yeah, in this subinterval, it will not be optimal to surrender. And we can see it in an example, a numerical example. In this example, we only use fee functions and surrender charge functions that depend on time. We don't have a state dependence. They exist in the literature. I'm working on an additional example here. But in this example, in example 1, this function here is quadratic in time. And what happens is that the term that I called L, I should have written that, but this term changes sign twice from 0 to maturity. And in the second case, we have a linear function, so the term changes sign only once. And we see it in the optimal surrender region. So the surrender region in this case is in white. So and the value of the initial value of the account is at 100 and the guarantee is at 100. So we see that surrender can occur for high values of the investment. And what's interesting is that we see that the surrender here disappears for some time during the life of the contract, and it's really just in 2 periods where you have optimal surrender. In this other case, we had this change of sign only once, and in this case, the surrender region just disappears. We see that the sign probably changes around here, and at this point, there's no more optimal surrender that can occur after this certain point. And some concluding remarks. So at the same time as we were working on this paper, we realized that Tiziano De Angelis and other co-authors were working on a very similar problem, which was a bit stressful, to be honest. But so and it's a very nice paper. They're working only with the constant fee rate, but looking at their work was very interesting because they confirm some of the results that we have. They have further assumptions on the surrender charge. Some of the results depend on the monotonicity of the optimal stopping boundary. So this makes this problem even more interesting to study because of this non-monotonicity. Like I said, I guess many times during the talk, our contribution also has applications when we develop numerical methods. That was a bit, in this case, also our goal, because initially we wanted to look at this problem, but for a more sophisticated market model, basically with stochastic volatility. After doing this work, we also realized that results of this type, so theoretical results like this for stochastic volatility models, are also very scarce in the case of American options. So it makes sense that it was harder for us to work on the case with stochastic volatility. That's something that eventually we'll want to do. But just in case of this simple geometric Brownian motion market, there are still questions that need to be answered. And so this is my some work that I will do in the future. Thank you very much for your attention.